So we're going to start with exponential functions. Exponential functions means that we have a variable in the exponent. Okay? So when you hear exponential function, what do you think is happening? What would happen to a number if it increases exponentially? It gets bigger and bigger, and then suddenly it's going to get bigger and bigger and bigger even faster. So here's an idea of an exponential function of y equals 2 to the x. It's a very basic exponential function, and I just want us to take a look at it and get an idea of what the exponential curve looks like. So we're just going to do a simple xy chart for this and think of our laws of exponents to help us out. We'll actually start down at, with the positive numbers, and we'll work our way negative. So if your x is 3, so if you take 2 to the third power, what do we have? Yeah, 2 to the third is 8. Here, 2 to the second power, or 2 squared. What's 2 squared? 4. 2 to the first power would just be 2, right? What would 2 to the 1/2 be? So 2 to the 1/2 is about, what did you say, 1 point? What did you get? I just didn't hear you. 1.4 about? Okay, or the square root of 2. What would be 2 to the 0? Not 0, no. No, 1. Anything to the 0 power is always 1. Okay, so now what happens with our negative exponents? Who remembers? It gets smaller, so it takes the value and it brings it where? Into the denominator. So what would be 2 to the negative 1? What does the negative exponent do? You just said it brings it to the denominator, so it becomes 1/2. So what would be 2 to the negative 2? 1/4. What would be 2 to the negative 3? 1/8. Okay, are we ever going to be able to get a negative number here? Nope. Okay, we'll never be able to get a negative. We're just going to get closer and closer to 0 the further negative we go. So if we graph these few points here, let's see here, we have at negative 3 we're at 1/8, so pretty small. At negative 2 we're at 1/4. Negative 1 we're at 1/2. 0 we're at 1. 1/2 we're at about 1.4. 1 we're at 2. 2 we're at 4. 3 we're at 8. So you guys see how this curve, it starts increasing just a little bit, and then suddenly it like makes a turn and jets straight upward. So that's what exponential growth means, or an exponential graph means. It means it starts growing just kind of slowly at first, slowly growing, and then suddenly it's going to take a turn, and it's going to grow super, super fast, really, really quickly. Okay, so we'll be dealing with these types of functions. So I do want you to know a few properties of these functions and what they mean and where they go with, and then we're going to do some algebraic manipulations with them today. This is just information about it. So here's our exponential function. Y equals a b to the x. We just did a b to the x one, so we did 2 to the x power. Okay? You can print this off online. It's there. So if you don't want to write it down, you don't have to. You can just go print it off. Y equals a b to the x. A can't be 0. Okay, what would happen if a were 0? The whole thing would be 0. Then it's no longer an exponential function. So a can't be 0. B has to be greater than 1. Or greater than 0, sorry. B has to be greater than 0. What would happen if B were less than 0? If B were a negative number? What happens when we take negative numbers to exponents? Like, oh, let's use negative 2. What's negative 2 squared? 4. What's negative 2 to the third? Negative 8. What would be negative 2 to the fourth? Positive 16. So this graph would be up and then a negative number, then a positive, then a negative, then a positive, then a negative. So taking negative numbers to exponents don't work. It's not going to give us that continuous function. So it's got to be positive. And b can't equal 1. Well, what would be the problem with b equaling 1? Yeah, here, if b is 1, if we go 1 to any power, it's always 1. So it wouldn't actually be an exponential function. Okay, so those are just restrictions so that we actually get that exponential function. And b is called the base number. Okay, so we're going to refer to that number that's being raised to an exponent as the base. We'll refer to it like that throughout the whole thing. Let's see if you guys remember these words. Function is continuous. What does that mean? It keeps going, so we can start. We can use our pencil to keep drawing it. We don't have to lift our pencil up anywhere. We can draw the whole function. Okay? And it's 1-to-1. Who remembers what 1-to-1 means? 6 is way back to September. 1-to-1 means that for every value, for every x or y value, there's only 1 point. So here, if x is negative 2, it only goes to 1 spot. But it also works that way for y. So if y is 4, it only goes to 1 location. So x's and y's only have mapped to one other value. The domain is always a set of real numbers. So what does that mean? What types of numbers can our x be? Positive and negative. Our x can be anything we want it to be. And the x-axis is always an asymptote because we can't have negative numbers. Whenever we raise things to an exponent, it's always going to be positive. So our x-axis works as an asymptote, meaning here's our x-axis. So this works as an asymptote. We're going to get closer and closer and closer to it, but we're never actually going to cross it. We're never actually going to touch it. That also tells us that our range would not include any negative numbers. It would only be positive. Oh, and that's the next thing. The range is a set of all positive numbers. You can have a set of all negative numbers if we're not growing, if we're decaying. Because if we're decaying, the graph, instead of going up, would be going down. Okay, it'd be the same thing, just flipped over. And you always know what the y-intercept is because the y-intercept is your a value. It's whatever is being multiplied by out front. So here, with the one that we graphed, there wasn't another number out in front, so we viewed it as 1. So that means your y-intercept here should have been 1. If I were to instead have changed this just a little bit and said y equals 3 times 2 to the x, now your y-intercept would have been 3, but otherwise it would have been the same exact curve, just up 3. Okay? But there's not, because the 2 is being raised to the exponent, so the number being multiplied to both of those is a 1 out in front. So it's whatever number is not attached to the exponent. And then the growth and decay. Growth, that b value here, or the graphs of y equals a b to the x and y equals a 1 over b to the x, they're reflections across the y-axis. So if you imagine going to the y-axis, if you reflected it, that would be a reflection across the y-axis. So this graph would be like 1/2 to the x. This would be reflected across it. Okay. And then we can have growth or decay. Growth is your a has to be greater than 0. Ooh, the sign is definitely wrong. And b has to be greater than 1 for it to be growth. For it to be exponential decay, your a is still greater than 0, but this time your b value lies in between 0 and 1, so it's some sort of fraction or decimal, like a half, a third, a fourth, something like that. And then we would have decay, which would be like this green line. That's a decaying line because it's going down. And the last section we do in this chapter, we'll deal more with the decay and the growth and how they relate to problems that happen everywhere.
Does the decay always go from the left to the right?
Yep. Yeah, the decay will always start up high and go low. So when you're looking from left to right, it should start high and go low. And the growth would always start low and go high. All right, so there's just some information about it. So if I give you an equation, we should be able to kind of sketch what it sort of looks like, okay, just based off this information. And so that's what we'll do for the next ones. The next ones we're going to decide if it's growth or decay, and then we'll just do a little quick sketch of what it should look like, okay? And it doesn't have to be exact. It would just be something like exponential growth. We know it should look like that. We know it looks like that. And then we also know that should not be where your y-axis is. And then we would also know what that point is, because that point would be whatever your a value was. Okay? So we'll just do very little sketches of it. So we want to decide if these are growth or decay. Grown. Oh, goodness. Growth or decay. So what we're going to do is we are going to look at the number that's being raised to the x value. Okay, so we look at this number here. We're growing if it's greater than 1, and we're decaying if it's in between 0 and 1. All right, so this first one, y equals 0.7 to the x power. We're decaying. Okay, so this would be decay. Then we're going to sketch just a little graph of what this should look like. So we have to determine what number is in front. So what number? There's a 1. So that means because that's a 1, you would cross the y-axis at 1. And then you would start up high, and you'd go low. So there's a sketch of what the decay should look like. Like I said, we're just sketching. We're not getting any more exact than that. Okay? We know it goes to the right because decays are always going to start up higher, and it's decaying. So we should have less and less and less and less and less of it. Okay?
So if there were another number in front of that, then we would have to start, like if there were 2?
Then we would start at 2 at the y, and we'd make sure we go through it. Okay? So example 2, y equals 1/2 and then 3 to the x. So first off, we have to decide if this is growth or if this is decay. This is growth. We know it's growth because 3 is greater than 1. So it's growth. So we'll sketch a little graph of what the growth should look like. What number is out in front of this one? A half. So that means on our graph, we have to cross at a half. And we're growing, so we're going to start low, and we're going to go high. I marked 1, and then I just put a little dot in between for a half, because we're just doing quick sketches of them. We're not doing anything exact. So let's see if we can do this third one then. Growth or decay, and then we want to sketch it a little bit. So y equals 10, and then 4/3 to the x. It's growth. Now, this one's a little tricky because it's a fraction, right? But it's 4/3, which is greater than 1. So it would have to be growth. And then where would we start at the y-intercept? The y-intercept would be where here? At 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there would be my y-intercept. And there would be the growth. What? Oh, yeah, you could. I'm also fine if you just go like this and then just say, oh, that's 10. And I'm going to go right from there. Because these are just sketches. I just want you to know what growth and what decay looks like. Okay? Is that okay? Get the idea of what they look like? And I'll make sure that those notes are up there with, and I will fix that typo and I'll re-upload them so that you'll actually have the right information on there. All right? So if you want to print those off, you can do that later. So now let's do some algebraic manipulations with this. Okay? We're going to simplify. This is really just remembering what our laws of exponents say. That's all we're doing here. Okay, we have to remember what our laws of exponents say. So we have to remember when we would add them, when we would subtract, when we would multiply, when we would divide. So maybe I'll write a little refresher over here on our laws of exponents. What do we do? Let's see. What do we do when we multiply two values that have the same base number? You add them. So this would be a to the x plus y. What do you do when you divide? You subtract. So this would be a to the x minus y. And what do you do when you have it a power to a power? You multiply a to the xy. So this first one, what operation do we have going on here? We're dividing. And now the way how this works is you have to have the same base number. These both have base numbers of 5. So what should I do with the two exponents? Subtract. So we just say 5 to the square root of 3 minus the square root of 2. No, we would just leave it like that. Okay? Okay, number 5 says 6 to the square root of 5 and then to the square root of 6. So we'd have to, what would we have to do with those two values? Multiply, so this would be 6 to the what? Yep, to the square root of 30. Then we're just going to leave it like that. Because we have an exponent to an exponent, so we would end up multiplying them. Okay, 6 gets a little trickier because the base numbers aren't the same. So this is 81 to the square root of 2 divided by 3 to the square root of 2. So in order for us to be able to use our laws of exponents, these two base numbers have to be identical. Okay? So if they don't start off the same, we need to make them the same. So look at your smaller number here, 3. Is this base number? Is there a way how we could make 81 out of 3s? 3 to the what power would give you 81? So what you want to think here is we want 81 to have a base power of 3. So you want to be thinking 3 to the what power gives you 81? 3 to the 4th power gives you 81. So since 3 to the 4th power gives you 81, you are going to rewrite this as 3 to the 4th, and then we still have the square root of 2. Divided by 3 to the square root of 2. Okay? Because we need that same base number. Now that we have the same base number, what can I do with those two? Subtract. So what's 4 square root of 2 minus square root of 2? Yeah, just 3 square root of 2. So 3 to the 3 square root of 2. How do we what? 4 minus 1 is?
How come you don't subtract what's inside the roots?
We don't. The square roots are they're like terms. It's just like we did a whole unit on square roots. Same rules apply now as what they did then. All right, is that okay? All right, let's try a couple more. So if we're going to solve these. Okay. These look like they're a little, they look like they'd be really hard to solve, but they're actually not. Okay. But when you look at this problem, you probably look at it and panic a little bit because we have a bunch of variables in the exponents. But they're actually not that difficult to solve. All what we need to do here is we need to get their base numbers the same. So we want both of these to have the same exact base number. Okay, because if I had 2 to the x is equal to 2 to the 5, what would x have to be? 5. X would have to be 5, right? So if your base numbers are the same, you can just make a simple equation out of your exponents. Okay, so you want to look at your numbers that you have. So here we have 4 and we have 256. And you want to decide what's the base number you could do. So 4. 4 is what? Is 2 squared. Okay, so we're going to rewrite 4 as 2 squared. And then we would still have 9n minus 2. Equals 256. 2 to the what power? To the 8th power? I think that's right. I'm just going to double check you. All right, so that's 2 to the 8th. So we're going to rewrite that as 2 to the 8th. Okay, so we brought them down to the smallest exponents that we could. Now these both have 2's, so I can just make an equation out of the exponents. So I can just say 2 times 9n minus 2 is equal to 8. Is there anything I could do with that 2 in the parentheses right away? I could probably distribute it out in the first step. So we could say 18n minus 4 is equal to 8. And then we just solve this. So how would we solve it? Add the 4. So 18n is equal to 12. Divide by 18. So n is equal to 2/3. And there we go. Is that okay? All right, so let's look at 8. 8 is 3 to the 5x is equal to 9 to the 2x minus 1. So in order for this to work, I need the same base numbers. 3, is there anything I can do with the 3? No, it's already as low as it can go. So how about the 9? Is 3 squared. Okay, so I'm going to leave 3 to the 5x alone. And I'm going to change the 9 here to say 3 squared. And then times your 2x minus 1. Now our two base numbers are both 3. So what can I do with the stuff in the exponents? Set them equal. Okay, so I would say 5x is equal to 4x minus 2. Subtract the 4x, so we have, so x equals negative 2. Is that okay? All right, one last one. 5 to the 3 minus 2k is greater than 1 over 625. Inequality signs, we do the same way as we do an equal sign. It's not going to change how we solve it, so we leave the inequality sign there. 5. Is there any way how we can make 5 smaller with exponents? Okay? 625. How can we rewrite 625? 1 over 5 to the...
Big number 7, 8, 9, 4, 5.
Now it sounds like you're guessing.
Yes, it's obviously 6. 7, maybe. Give me a calculator.
To the what? To the fourth. Well, I know you said 4, but you also said 5 and 9 and 3. And so I was waiting until you were like 5 to the 4th. I know that was certainty. Now, right now the 5 to the 4th, though, this is in the denominator. So how could we write this in the numerator?
Negative?
Yeah, you just make it a negative exponent. So that means it'll move it up. So you'd have 5 to the 3 minus 2k is greater than 5 to the negative 4th. Okay? The negative sign just tells us that we were in the denominator. Okay, so now what equation could we make here to solve this?
3 minus 2k equals negative 4.
Is greater than negative 4. All right? What would we do to solve?
Add the 3.
Subtract the 3 over? So we have negative 2k is greater than negative 7. Divide by your negative 2, and then what happens? K is less than.
Oh yeah, because when you divide.
You can just leave it 7 halves. Yeah, when you divide by a negative, you got to make sure you flip the sign around. All right, is this okay? All right.